Now let us study excitation table of the JK flip-flop. So this excitation table is required if you are designing any synchronous counter with JK flip-flop. So this is a truth table of JK flip-flop. Okay. Here I am assuming my JK flip-flop is a negative ST card. So if JK inputs are 0 0, it remains in a last state. When JK inputs are 0 1, then it gets reset. When JK input is 1 0, it gets set, and when JK inputs both are 1 1, then it toggles. This is a truth table of a JK flip-flop, which already you have studied. Now the excitation table is derived from this truth table. Now in excitation table, if present state is 0 and next state you want 0, means flip-flop is in reset condition, and in next clock cycle also, if you want flip-flop to be in a reset condition, what input you have to give. Okay. Now if you observe here truth table, okay, if inputs are 0 0, then it remains in a last state. Okay, now last state is here 0. Okay, so if inputs are 0 0, then also it will remain in a 0 state. This is a one condition. Another condition is when inputs are 0 1, okay, then also it will get reset. Okay, so here we want the flip-flop to be reset in the next clock cycle. So even this input will do. So here, so these two inputs we can give. So here J has to be 0, but K can be 0 or 1. That's why for this we can write 0x. X means 0 or 1. Okay. Similarly, if present state is 0 and next state we want 1. Okay. Then what input you have to give? Now here from the truth table, now next state I want 1. So here if I give a input 1 0, okay, it will get set. So that is what we want. So this 1 0 will also do. Also, if inputs are 1 1, it gets toggled. Okay, so here present state is 0 and next state you want 1. So here toggling is there. So here this input will also do, as well as this input will also do. So here means J has to be 1, but K can be 0 or 1. Means we can write here 1x. So here for going from 0 to 1, the input will be 1x. Like that. Present state is 1 and next state we want 0. Now here this input will also do, as well as this input will also do, because here toggling is there. So if you observe these two, this and this, K has to be 1, but J can be 0 or 1, means x1. So that's why for 1 0 it is x1. Then present state 1 and next state also we want 1. So what input is required? Okay, so this 0 0 will do, because present state and next state is same. So 0 0 will also do, as well as we want 1, means this input will also do 1 0. So if you observe this and this, okay, K has to be 0, but J can be x. So x0. So here x0. So this is a excitation table of a JK flip-flop. So this is required if you are designing any synchronous counter using JK flip-flop. So now let us design mod 4 synchronous counter using JK flip-flop. Mod 4 synchronous counter using JK flip-flop. So here this 4 is less than equal to 2 raised to 2. This is not equal to 2 raised to 1. This equation will not satisfy for 2 raised to 1. So that's why 1 flip-flop is not sufficient for mod 4, but 4 is less than equal to 2 raised to 2. So now here for 2 raised to 2 the condition satisfies. That's why minimum 2 flip-flops are required for this counter. Okay, so this counter will count from 0 to 1, 1 to 2, 2 to 3, and again it will start from 0. So this 4, it goes through these 4 states. That's why it's a mod 4 counter. Okay, now here instead of writing this way, present state and next state, I will write this way. Now you can write this way or that way. So here counter has to count from 0 0 to 0 1, then 1 0, and then 1 1, and from 1 1 it has to go to 0 0. So this is a counting sequence of the counter. Okay, now if you observe here, see here, while going from this state to this state, Q1 has to go from 0 to 1. So what input you have to give from the excitation table? While going from 0 to 1, the input required for flip-flop 1 is 1x. Okay, this is from excitation table. Then next, while going from this state to this state, okay, Q1 again has to change from 1 to 0. That's why the input required is x1. This is also from excitation table. Then next it has to go from 0 to 1. So 1x is the input, and then it has to go from 1 to 0. So the input is x1. Like that you find out for J2 K2 by observing this. Now it has to go from 0 to 0, so input required is 0x. Then it has to go from 0 to 1, so input is 1x. Then it has to go from 1 to 1, so input is x0. Then it has to go from 1 to 0, so input required is x1. So now this is a basically truth table for input logic. Okay, now in a synchronous counter we design a circuit for giving the inputs. Okay, and output of counter we use as an input. Okay, then K-map for J1. Okay, so these values we have to enter in a K-map. Okay, so here just two variable K-map, Q to Q1, and these values are entered because this is the K-map for J1. So the expression here you can combine all 4 cells, so J1 will be logic 1. Similarly, these values you can enter in a K-map for K1. So here also 4 cell you can combine and K1 will be logic 1. Then these values, J2 values, you can enter in a K-map for J2. So here you can combine only these 2 cells. So the expression will be J2 equal to Q1. Okay. Similarly, we can have a K-map for K2, and these values you can enter. So now here also we can combine only 2 cells. These 2 cells, and the expression will be again same. Q2 will be Q1. Q2 will be Q1. And then we can have a logic diagram. So here two flip-flops are required, so we are using JK flip-flops. So here two JK flip-flops. So being synchronous, clock is given simultaneously to the both the flip-flops. Okay, so clock is given here J1 K1 we got expression logic 1, so that's why logic 1 is given, and J2 K2 we got expression Q1, so here Q1 is given to the J2. So here output is taken from Q1 Q2, so here you will get a count, and clear input is shorted and connected to logic 1 while it is counting. If it is connected to 0 or if 0 pulse is given, it is get clear. Okay, but here we don't use a reset logic. Okay, so this is a mod 4 synchronous counter.